With the module-based implementation of partial reconfiguration, we are gaining all the advantages of the widely used modular design approach. It is a design approach that allows several designers to cooperatively work on the same project simultaneously. This approach implies that the team of designers needs to have a leader in charge of organizing the system into modules. By doing this, him or her has to estimate the amount of resources that will be used by each module, defines the placement location for the modules on the device, and lets the single part to be developed by the other designers independently. Within this context, we can see that this approach is basically recalling the structural VHDL Verilog design of a system. By embracing this design methodology, we are allowing per module a parallel and independent design entry and synthesis, design implementation, design verification. But at the same time, we have to be very careful at the system level to take care of the following design constraints: module definition, module height and width, inter-module communication. Now, as we can understand, this approach is definitely interesting to implement a partial reconfigurable system. We can use the modules to define our reconfigurable functional units and the module placement constraints to identify a reconfigurable region. The reconfiguration is going to happen because we may have two or more modules implemented in the same area. This solution has specific limitation constraints. Reconfigurable regions have strict shape requirements, which basically means that we cannot assign height and width in a completely arbitrary way to our reconfigurable regions. Bus macro replication. We need to guarantee the correct crossing of modules boundaries by using a set of macros that have to be instantiated in our design. The identification and definition of the area constraints also for the part of the design that won't be affected by reconfiguration of other elements. We can see this as the static side of our system. It's quite typical in the case of design of a partial dynamic reconfigurable system in using the static side to implement the reconfiguration controller or manager if you want. The module-based design flow is organized in four main steps: HDL description and synthesis, initial budgeting phase, active module phase, final assembly phase. During the HDL description and synthesis step, the designers in the team develop their own modules using hardware description language and synthesize them by using synthesis tools. During this phase, the team leader has the role of designing the top-level design entry and synthesize it before moving to the initial budgeting phase. It's important to notice that at the top level, all global logic has to be included. All the modules are instantiated as black boxes with only the information on their interfaces. All the signals connecting all the modules must be defined. During the initial budgeting phase, we are defining design constraints. As an example, during this phase, we are going to identify the area constraints for each area used to implement a module. This is what we are used to refer to as the floor planning phase. The active module phase is where each component is going to be implemented. Thanks to the constraints identified during the initial budgeting phase, we can independently implement each module composing our design. Just to be clear, by implementing, I'm referring to the technology mapping and the place and route phases. The results of the active module phase can be seen in this picture. What we are observing is the design of three different modules. Two of them, the smallest ones, are used to configure two modules that are used to realize two reconfigurable functional units. I did also highlighted reconfigurable regions with a rectangular box surrounding the RFU, while the third one is the module used to implement the static element of our system. Once we have all the modules implementations, we are ready to go through the final assembly phase, which is used to assemble individual modules together to create all the necessary configurations used to generate all the necessary partial bitstream. In our examples, we are creating an initial configuration bitstream with only the static side and two partial reconfiguration bitstreams, one for a configurable functional unit. And in this figure, we can see a possible configuration of our system, where we can see both the reconfigurable functional units simultaneously implemented on our system.